Welcome to a world where pixels and creativity converge. In this video, we embark on a journey that fuses the timeless charm of 2D pixel art with the cutting-edge power of 3D rendering. I initiated this research with a design influenced by practice-based research. Practice-based research entails the parallel execution of practical projects and research activities, creating a symbiotic relationship between these elements. This interconnected approach nurtures the emergence of innovative and original forms of knowledge. To intertwine my research with the community, I strategically integrated my practices into workshops, disseminating them across relevant communities. This dissemination aimed to share my findings in 3D altering pixel art, facilitating learning for a broader audience while encouraging valuable feedback on my practices. Regarding pixel art, according to Daniel Silber in the book Pixel Art for Game Developers, pixel art, an image where each pixel visible on screen is placed intentionally. Key characteristics of pixel art, distinguished from 3D art, vector images, and traditional paintings scanned into computers. The fundamental distinction lies in whether the individual pixels are visually evident to the human eye. For instance, vector images require significant enlargement to reveal their pixels, thus they do not qualify as pixel art. At the research's outset, the researcher delved into the possibilities of merging 3D rendering with 2D pixel art, discovering that pixel-style materials have the capacity to harmonize with 3D realistic environments, imbuing pixel-style objects with enhanced vitality. This initial research phase unequivocally confirmed the transformative influence of 3D rendering on 2D pixel art, offering a distinctive visual experience. This pivotal observation precipitated a shift in the research question, redirecting the focus toward elucidating the mechanisms through which the 3D rendering process alters 2D pixel art. Following this, the research unfolded with 3 experimental practices aimed at further exploring the domain of 3D rendering's impact on 2D pixel art. These practices encompassed: Experiment Practice 1, involving model block transform voxelization. Experiment Practice 2, focused on pixelation filters. And Experiment Practice 3, which revolved around the utilization of normal maps and assorted textures to alter pixel art. In the first practice, we started with a cylindrical object featuring intricate triangular patterns on its surface. Setting the octree depth to 7 allowed us to capture fine details effectively. However, when we reduced it to 6, we noticed some loss of detail. Second test. Next, we moved on to a smaller component, initially assuming that an octree depth of 7 would work well for all object sizes. Surprisingly, for this particular component, an octree depth of 6 provided excellent detail representation. In fact, even when using an octree depth of 5, the smaller component still retained its fine details remarkably well. Third test. For our third experiment, we integrated the smaller component with the overall object, creating a large component with finer details. This time, using an octree depth of 5 severely distorted the appearance of the larger component, while going up to 7 restored its shape. However, this change led to a loss of detail in the smaller component. It was only when we tried an octree depth of 10 that the finer details of the smaller component were accurately represented. Outcome. These tests revealed a significant pattern. The effectiveness of octree depth in capturing object details depends on the overall size of the object silhouette and the size of its finer details. Larger objects with smaller details require a higher octree depth value to accurately depict the object's appearance. To optimize your modeling process, it's advisable to separate objects with intricate details from larger ones and assign them different appropriate octree depths. This will help achieve the best results in rendering your 3D models. The next section focuses on the application of insights gained from voxelizing the mechanical deconstruction model to character voxelization. The testing process has unveiled 4 key findings. Finding 1, voxelizing patterns featuring gaps can result in the loss of certain pattern elements. In Character Test 1, we can see 2 pattern examples with gaps, and some parts of these patterns are not adequately preserved during the voxelization process. Finding 2, thin and curved models, especially those like the character's hood and belt, are prone to developing holes during voxelization. Adjusting the scale value can impact the location of these holes, adding a weathered or worn appearance to the character. This is evident in Character Test 2. Finding 3, replicating the original facial model's appearance through block remesh can be quite challenging. However, it does offer the advantage of allowing the model to adopt various styles. In Character Test 3, we explore the presentation of the facial model at different octree depth values. Finding 4, when models of the same color overlap, they can become less distinct after block remesh. To create contrast and distinction, one can assign different colors to two overlapping parts, or apply significantly different octree depth values. Character Test 4 effectively demonstrates the impact of assigning vastly different octree depth values to two parts, emphasizing the contrast between them. Finally, let's discuss the scale value. Scale value, as mentioned in our previous tests, refers to the maximum value of 0.9 that can be selected within Blender's remesh block function. This parameter is crucial for controlling how blocks are arranged during voxelization. By adjusting the scale value, you have the ability to either emphasize or conceal specific visual details of the model while keeping the current octree depth setting. For instance, when dealing with mechanical block-type models, you can use the scale value to fine-tune how blocks are arranged, allowing you to highlight or hide particular model details. In the context of fabric structures or similar models, adjusting the scale value can also be helpful in concealing certain damages or worn-out areas, giving you more control over the voxelization process. To the second practice, we're diving into the fascinating world of pixelation filters. This experiment took place right here in Blender, using the remarkable pixel art rendering plugin developed by Lucas Rodel. Now, a quick note. Our observations and results are tailored specifically to the 3D alteration of 2D pixel art within the Blender environment, utilizing the pixel art rendering plugin. Let's uncover the magic of pixelation and how it transforms our 3D models into pixelated wonders. Ready to pixelate? Let's get started. Testing process. Let's dive into the testing process. I approached this with a combination of practice and observation. First, I ventured into the vast realm of online resources to explore how to render objects in that delightful pixel art style right here in Blender. My quest uncovered two promising methods. The first method was all about procedural filters, and the second introduced me to the enchanting world of pixelation plugins. Armed with this knowledge, I embarked on transforming a character into a captivating pixel art masterpiece. Let me break down the specific procedure for using the procedural filter. Within Blender's compositor interface, you'll want to navigate to the render layers, which essentially represent the final rendering output. Now, this is where the magic happens. Add a Pixelate node into the mix. This nifty node takes your original image and performs its pixelation sorcery, resulting in that charming pixel art effect. Now, let's talk about the pixelation plugin. This handy tool comes in two parts. First, there's the pixelated renderer, and secondly, there's a module that lets you tweak the way textures are shaded. It takes those smooth gradients of light and turns them into multi-tiered, hard-edged transitions. To illustrate, we've got a side-by-side comparison for you. On the left, you can see the texture shading method provided by the plugin, while on the right, it's Blender's original texture shading effect. The mastermind behind this plugin is Lucas Rodel. If you're interested, you can find and get your hands on this plugin at the following address. After wrapping up the practice, I moved on to the testing phase. Here's what I tested. First one, texture color, both in low saturation and high saturation. The second, different texture comparing smooth gradient lighting texture with multi-tiered hard transitions lighting texture. The third, different renderers, including Eevee, Cycles, and the Pixel Renderer. The fourth, direct rendering by renderers versus using procedural filters. The fifth, testing with and without contour lines. The last, lighting. These tests were crucial in understanding how various factors affect the final pixelated image. Following the creative process, I uncovered numerous potential factors that could impact the resulting pixelated images. Utilizing a practice-based approach, I delved into the exploration of these factors. After this exploratory phase, I generated a wide range of pixel art outcomes. Subsequently, I systematically organized and analyzed these outcomes to identify the factors that influenced the visual results. The next part will introduce the findings derived from the observation tests. Experiment 1, Texture Color Variations. In this experiment, I explored the impact of texture-color variations, specifically examining settings for low saturation and high saturation. Through careful observation, I discovered that different color combinations can evoke distinct visual experiences. For instance, low saturation settings can create a nostalgic, retro video game rendering, while richer and more saturated colors give rise to a modern pixel art style. Therefore, it's essential to consider texture design before applying filters, as it can significantly influence the final filtered outcome. The second factor is texture lighting systems. In my exploration of texture lighting, I experimented with two modes, smooth gradient lighting and multi-tiered hard transitions, to observe their impact on the final pixelated outcome. The results indicate that smooth gradient lighting contributes to a more realistic appearance. Conversely, multi-tiered hard transitions introduce a stylized effect, providing the image with a vintage and classic aesthetic. The third aspect I explored is different renderers. I conducted tests using various renderers, including Eevee, Cycles, and the Pixel Renderer, to gauge the variances in their rendering capabilities. I found that when using the Cycles renderer, it's not possible to enable the model's outline feature, and using the plugin's texture rendering method can result in a washed-out color appearance. However, Cycles excels in rendering with more precise ray tracing effects, offering a more realistic look with features like transparent and refractive materials. Therefore, for pixel art projects where complex lighting effects are crucial, Cycles is the recommended renderer. On the other hand, Eevee stands out for its faster and more efficient rendering, with a more cartoon-like rendering style. It also provides the option to enable the model's outline feature, which can emphasize the stylized appearance of the artwork. Direct rendering versus procedural filters. I compared the outcomes of direct rendering by renderers with those achieved through procedural filters, aiming to reveal any disparities. After the comparison, I found that there is no difference in the pixelated images when using direct rendering versus procedural filters. The last finding concerns the presence or absence of contour lines. To understand the significance of contour lines, I assessed how their presence or absence influenced the pixelated images. The use of contour lines can impart a different style to pixel art. Contour lines make the model's outline more prominent, creating a stylized effect. Conversely, the absence of contour lines accentuates the contrast between light and dark colors, directing the viewer's focus more toward the colors and geometry of the image. To the third practice. Now, let's delve into the experimental process. I began this experiment following the practice-related research approach, aiming to explore potential knowledge and issues. My task was to create a simple pixelated wand, enhancing its pixel art effect using a normal map. In the first attempt, I tried constructing a 3D version of the wand over the original image as a reference, then baked its normal map. Unfortunately, this initial experiment ended in failure. The method proved challenging to control, making it difficult to create a wand perfectly aligned in size with the background image. Additionally, adjusting the model after building it became cumbersome. An error in the lower part of the baked pattern further compounded the issues. We will explore the reasons behind these problems later in this process. Eventually, I decided to abandon this approach, so my conclusion is to not recommend using this method. In the second attempt, I manually cut out squares on the mesh and adjusted the heights of vertices, edges, and faces. However, this approach presented two significant issues. First, due to manual alignment with the reference image in the background, the final product couldn't perfectly match the pixels in the reference image. This required meticulous inspection of areas with misalignment and readjustment. Second, when I adjusted the model's protruding parts, triangular faces appeared, leading to the creation of triangles. We'll delve into the reasons behind triangular faces and how to address them in the following sections. To address the alignment and height adjustment issues, I embarked on the third practice. To ensure alignment with the background image, I used a method where the number of face cuts was set to the pixel image's resolution -1. For instance, if the pixel image was 32 by 32, I cut the faces 31 times to achieve precise alignment. Following this, I adjusted the height of each face. The final result was that every pixel was accurately matched. This method proved to be highly suitable. Simultaneously, in this third practice, I attempted to remove the background region for model baking, which ultimately led to a problematic normal map, as shown in the figure. The next part is about the problems that we met during the experiment. Problem 1, triangular faces. In this experiment, I created a face and subdivided it into 9 smaller faces, with the central one marked in red for clarity. As I adjusted the heights of the points, edges, and faces within the red central face, I closely observed the outcomes. Here's what I discovered. The first one, it's crucial to ensure that within a single face, no individual point should have a different height compared to the other 3 points. The second one is, for the 4 points of each face, it's essential to make sure that a single point shares its height with one of its adjacent points. For example, if one point on the red face is elevated compared to the other 3 points, it results in the creation of triangular faces, as depicted in the image. There are 2 methods to address the issue. When ensuring that neighboring points within the same face have at least one point at the same height, the red face no longer produces triangular faces. However, an issue arises when the neighboring faces fail to meet this condition. As a result, triangular faces emerge in the adjacent faces. This phenomenon is explained in detail in the following part of the workshop video. To resolve the issue described above, there are 2 methods. The first method involves isolating the red face from the others and then adjusting its height. The second method entails extruding the red face and then modifying its height. In the ongoing experimentation with the 9-grid setup, where various modifications were applied before baking, here are the outcomes. 3 methods proved successful in achieving error-free bakes. These methods are as follows. 1. Keeping the background faces. 2. Keeping the adjacent background faces. 3. Removing the vertical faces while retaining the background faces. On the contrary, 4 methods led to baking errors during the process. These problematic methods include 1. Removing all background faces. 2. Filling the bottom. 3. Removing both the vertical and background faces. 4. Removing the main body. The normal map will disappear. This thorough experimentation unveiled specific approaches that ensure error-free baking, as well as those to be avoided. Finally, I proceeded with the 4th round of practice. This time, I adopted an approach that ensured the absence of triangular faces and baking errors. I retained the background portion except for the main body of the staff. Afterward, I successfully baked the one-sided model of the staff to obtain an accurate normal map. Additionally, I created metallic roughness, opacity, and emissive maps for it. When combined, they produce the following effect. This exemplifies the concept of 3D altering 2D pixel art. In closing, this research represents a transformative fusion of 3D rendering and 2D pixel art, pushing the creative boundaries in the pixel art community. Through practice-based research and online workshop videos, we've revealed key insights, addressing challenges and enhancing pixel art aesthetics. Our aim is to reshape the future of pixel art, offering innovative approaches and uniting 3D rendering with pixel art. Thank you for joining us on this exciting journey.